What's up, everybody? Let's get this Unit 6 on periodic trends started. Just so that we have a quick review of where we're at coming into this unit. Remember that we just talked about the periodic table and electron configurations, and we said that elements are organized according to their atomic number and electron configurations. So the number of energy levels determines what row on the table an atom is in. The number of electrons in the outermost energy level determines which vertical column it is in. So every element in the same row has the same number of energy levels. Everything in the same group vertically will have the same ending to its electron configuration. So for instance, everything in group 1 will end in the highest number, S1. So that's 1s1, 2s1, 3s1, 4s1, all the way down to 7s1. Everything in column 2 ends in an S2. So beryllium, for instance, would be 1s2, 2s2. Magnesium would be 1s2, 2s2, 2p6, 3s2. When we look at the vertical columns, every element in the same vertical column has the same ending to its electron configuration. The most important configuration to be aware of is the noble gas configuration, which is where the highest number S and P sublevels are filled. That means it has a full valence. The maximum number of electrons that can be in the valence shell is 8. So when we talk about valence electrons, we're talking about electrons in the highest energy level, S and P electrons. So if we look at 3s2, which is magnesium, it has a configuration of 1s2, 2s2, 2p6, 3s2. Look at the numbers out front. What's the highest number out front? The 3. So the third energy level is our valence, and the 3s2 are our only valence electrons. So magnesium has 2 valence electrons, and those electrons are found in the 3s sublevel. If we look at the next one, which is 4p3, 4p3 would be arsenic. We go through the entire configuration, and when we go back to figure out the number of valence electrons, we have to look at the numbers out front. 1, 2, 2, 3, 3, 4, 3, 4. So our highest energy level is 4. It's going to have 2s and 3p, a total of 5 valence electrons. The d electrons do not count in the valence. What energy level are they on? They're on the third. What's our valence energy level? The highest, 4th for this one. So keep that in mind. Same row, same number of energy levels, same column, same ending to their electron configurations. When we talk about a trend, we're talking about how something changes as we go from left to right on the periodic table. That's called the row trend. And the group trend is how something changes going from top to bottom. The 4 trends, and actually we'll say we're going to do 5 this time. And the last one is reactivity. Okay? Reactivity, electronegativity, ionization energy, ionic radius, and atomic radius. These are the 4 properties that we're going to observe trends for. We're going to get through atomic radius, ionic radius, and ionization energy this week. The rest of it, we'll kind of go deeper into ionization energy on Monday of next week, and then we'll finish up electronegativity and reactivity through the rest of the week. So if we look at atomic radius, the definition for atomic radius is half the distance between the nuclei of 2 atoms of the same element bonded together. The reason that we have to say that odd definition, we can't just say from the nucleus to the outside edge of the atom, is because there is no distinct or hard edge to the atom, right? Think about Bohr's electrons. Every time that any energy is absorbed, those electrons are jumping out and falling back. So there's a very good likelihood that what you're going to see is that the electron cloud of an atom is constantly expanding and contracting, expanding and contracting. So there is no definite hard edge. But what we did see is using Coulomb's law, which is that opposite charges attract, like charges repel, when we have two atoms of the same element that bond, at some point they end up settling on a distance that the nucleus spreads out. And what we do is once we see those atoms bonded together, we can see the nuclei using something called an electron tunneling microscope, really strong magnification. We can see the actual nuclei and we're able to measure them in what we call picometers, which is 10 to the negative 12 meters. It's really small. Or angstroms, which is 10 to the negative 10. Now, we know what the definition for atomic radius is, and what we want to focus on now is what is the trend across a row and why does that happen? And what we're going to see is it is going to relate or connect with nuclear charge going across the row. So if we go across a row, what we're going to see is that the atoms are going to get smaller. Even though they're getting heavier, they're going to get smaller as we go across from left to right. And the reason for that is that the atomic number increases the number of protons and the neutrons, of course, and that as the mass of the nucleus gets greater, its gravity becomes stronger and it's able to pull the electrons in tighter. The measure of this is called the nuclear charge, and it's shown as what we call ZF, so Zeph or Z effective. And the way that we calculate Z effective is we take the atomic number minus the core electrons. So that's everything that is not a valence electron, and that's going to give us our nuclear charge. Well, that just happens to be equal to the number of valence electrons. And as the number of valence electrons goes up, so does the Z effective, so does the gravity of the atom, and the atoms will shrink in size. So if we look at this kind of really crude drawing here, you can see that as we go from the first row, or first column, you'll see that the size of our atoms is shrinking as our mass of our nucleus goes up. So our row trend is as we move across a row from left to right, our atoms get smaller because the gravity of the nucleus that we refer to as our Z effective, our effective nuclear charge, is getting stronger and pulling those electrons in tighter. Now, the group trend depends on shielding. So we talked about nuclear charge being the gravity of the nucleus. Well, what is shielding? Shielding creates a building up, if you will. So if we look at the trend as we go from top to bottom in a group, the atoms get bigger. Building up principle would say, as we go down, each time we go from one row to two, two to three, three to four, four to five, and so on, all the way down to seven, what's happening is we're adding energy levels. And I don't care how strongly you pull two energy levels in, you're not going to make it smaller than one. 3 can't be smaller than 2, 4 can't be smaller than 3. So as we move down a group, you're adding energy levels, and no matter how much bigger that nucleus is, the extra energy levels are going to make the atom bigger. Now, the other way to look at this is called shielding. Shielding relates to how many electrons are in between the nucleus and the outer shell. So for row 1 elements, there is no shielding. There's no electrons in between. If we go to row 2, we have one layer of shielding. So there's a little bit of interference. There's a little bit of interference going from the nucleus to the electrons on the outer shell. So they're not held onto as tightly. When we look at the third row, we have 2 layers of shielding, 3 layers of shielding in row 4, 4 layers of shielding in row 5. So imagine layers of screen placed down in front of you, and you're trying to read through more and more layers of screen material. Doesn't matter how bright the object is, how big the object is behind it,
the more layers you put between you and that object you're trying to see through the screens, the less clear it is, the more of the image that gets blocked. It's the same thing with the nuclear charge. Even though the nucleus is bigger, we have more core electrons to interfere with it holding on to its valence. So as we go down, adding layers makes more shielding, makes the atoms get larger. The atomic radius increases as we go down. Now, when we look at
ions and their radius, what we don't have is a row trend or a group trend. Instead, what we have is a metal trend and a non-metal trend. In order to get our heads wrapped around, let's do a quick review. So remember, ions are atoms that have an overall charge because they gain or lose electrons to get a full S and P. So they're trying to get that noble gas configuration. They're trying to get a full highest energy level S and P sublevel. To do that, remember that every electron lost gives you a plus charge, and every electron gained gives you a -1 charge. Metals lose electrons and form positive, non-metals gain and form anions, negatives. So when we look at ionic radius, we define it as the distance from the nucleus to the edge of the ion cloud. And when we talk about the ion cloud, again, we're talking about looking at how much space it's occupying in a bonded scenario. We're not going to measure them as much as think about how would the size of the atom change when it ionizes. So cations have a smaller radius than their element. So the metal ions are smaller than their atoms because what's happening is you're looking at, let's say, an element that is in group 1 and group 1 row 2. So that would be lithium. Lithium wants to lose this electron. When it loses that electron, it loses that entire energy level. So what does it end up becoming? It ends up becoming the nucleus of lithium with helium's electron cloud. So now that atom has shrunk. When ions occur, when metals ionize, they shrink. When metals ionize, they shrink. If we have an element that, let's say, is in group 3, and let's say that this is our group 17 element. So we need one more electron for that thing to be looking just like argon. If an electron comes in, then what happens? Now you have the same nucleus trying to hold on to more electrons. When nonmetals ionize, they grow. When nonmetals ionize, they grow, and that's because you have the same nucleus trying to hold on to extra electrons. There's no decrease in shielding. There's no increase in shielding either, but the nuclear charge stays the same. We have actually less. The nuclear charge actually goes down a little bit, and that means that we have less gravity to hold on to more electrons. So the big picture here is that for ionic radius, we're talking about the size of the atom once an electron is gained or lost. The metal trend is that the atomic radius is bigger than the ionic radius because we lose electrons to become like the previous noble gas. They lose an entire energy level. Nonmetals, their trend is the ionic radius is bigger than the atomic radius because they gain electrons with the same nuclear strength that can't be held onto as tightly. So think of it this way. Metals shrink when they ionize, nonmetals grow. Metals shrink when they ionize. Nonmetals grow when they ionize.